So as a finale to Chem 241, we're going to talk about ring opening reactions of epoxides. So recall this COC ring structure over here is relatively unstable, has a lot of potential energy, so ring opening is a favorable exothermic process. And we can have ring opening in two different conditions. We have ring opening in basic conditions and in acidic conditions, and they'll result in qualitatively different products, so we're going to talk about both. So the first one we're going to talk about is the ring opening of epoxides in basic conditions, and this obeys typical SN2 dynamics. You have a nucleophile coming through, attacking the least substituted carbon, and then the leaving group, this oxygen here, leaving on the opposite end. So nucleophile comes in, backside attack, leaving group leaves from the front. All right, and that's the first step in ring opening in basic conditions. Second step, water comes in and is deprotonated, yielding in a hydroxide substituent group over here and a hydroxide anion. All right, so here are some common nucleophiles for ring opening of epoxides in basic conditions. So as I mentioned, this obeys typical SN2 dynamics. So you have backside attack of the nucleophile, and then you have front side leaving of the quote-unquote leaving group. It doesn't actually leave. It's not traditional leaving group, however. It does behave similar to standard SN2 leaving groups. So here we have a methoxide nucleophile coming in. It attacks our epoxide from the back end. Therefore, it's pointing downward in the final product. Our oxygen goes up from the front end, and therefore our OH group is pointing up in the product. And this is typical SN2 dynamics. All right. In terms of regiochemistry, nucleophile attacks the least substituted carbon, and this is standard for any SN2 reaction. Remember, in order to approach the backside, you want as little hindrance as possible. When you have minimal hindrance, the reaction is more favorable. And in this case, the least substituted carbon is going to be the less hindered one, and therefore the nucleophile is going to approach that carbon more readily. So that's an important point, that in ring opening in basic conditions, the nucleophile attaches to the least substituted carbon. Acid catalyzed, or not acid catalyzed, the ring opening in acidic conditions is a little bit different. So in acidic conditions, your first step is the protonation of the oxygen in the epoxide ring. This yields a positively charged oxygen, which itself is a relatively good leaving group. Then you subsequently have backside attack of the nucleophile on a carbon atom and subsequent leaving group of the OH group on the opposite side. So this looks like typical SN2, like a typical SN2 mechanism, but it's not. And we'll see why in the next section. So one thing I want to point out is when your nucleophile here is a halide, your final product is going to be what is called a vicinal halohydrin. A vicinal halohydrin generally is just any molecule in which you have a halide and an OH group on adjacent carbons. And I point this out because in basic conditions, a vicinal halohydrin will actually participate in the reverse reaction to form an epoxide. So one of the means of actually synthesizing epoxides is by treating vicinal halohydrins with a base, right? However, you don't need typical halide acids for this reaction to occur. You can use hydrocyanic acid as well. Any strong acid, really, with a good nucleophile. All right, so the stereochemistry of acidic opening is similar to that of basic opening. You have nucleophilic attack from the backside, and then you have the leaving group, in this case the OH group, leaving from the front side. So the nucleophile and the OH group are going to be trans to each other. And once again, this is the same as for ring opening in basic conditions. Regiochemistry is a little bit different, and that's because this partial positive charge on this protonated oxygen in the ring is distributed along this ring. And this carbon over here, in our example, will bear the bulk of the positive charge, because remember when we were discussing carbocations and discussing SN1 and E1 mechanisms, more highly substituted carbocations are more favorable. Now, the one thing is that carbocations are flat. So when we're talking about SN1 reactions, our nucleophile could attack from either face of the carbocation, and if we were to have SN1 substitution of a cyclic compound, we would end up with both cis and trans products in roughly equal distributions. That's not what happens in acidic ring opening of epoxides. In acidic ring opening of epoxides, we have the nucleophile attacking from the backside, our OH group, quote unquote, leaving from the front side. So we end up primarily with a trans product, just like we do in the SN2 ring opening in basic conditions. However, our final product has a little bit different regiochemistry in that the nucleophile will add primarily to the more substituted carbon. And it binds primarily to the more substituted carbon because that more substituted carbon bears the bulk of the positive charge, and therefore this nucleophile is more attracted to the more substituted carbon. And that's one thing you want to remember, that for ring opening in basic conditions and ring opening in acidic conditions, that the stereochemistry is the same, and that the OH group in the final product is on the side opposite of which the nucleophile is. They are trans to each other. However, the regiochemistry differs between ring opening in basic and acidic conditions. In basic conditions, the nucleophile will add to the less substituted carbon, and in acidic ring opening, the nucleophile adds to the more substituted carbon. And that essentially does it for Chem 241. Good luck with your studies.